Welcome to this explainer. Today, we're going to decode the precise scientific truth behind work and energy using the simple everyday actions we all do. You know, we toss around the words work and energy all the time, right? We say we're full of energy or that we've just put in a hard day's work. But in the realm of physics, these words have incredibly strict mathematical definitions. So get ready because today we are going to completely reshape how you view your own daily efforts.
Okay, here's our roadmap for today. We'll start with the science of work, look at when work is actually zero, dive into positive and negative work, explore the work-energy theorem, and finally, wrap up with kinetic energy and motion. Let's get right into it.
So let's kick things off with a bit of a puzzle. I want you to imagine pushing a solid, heavy brick wall. Just picture it. You plant your feet, you push with literally all your might, and you keep at it until your muscles are just completely exhausted. You're dripping with sweat. Now, you definitely feel like you've worked incredibly hard, right? But how much work would a physicist say you actually did on that wall?
Well, surprisingly, the strict scientific answer is exactly 0 joules. 0. Absolutely no work was done on that wall. I know it sounds crazy, but it's a shocking truth that brings us right to our first core concept. It really reveals the massive difference between biological effort and physical work. To really get this, we kind of have to strip away our everyday biases and look at the universe completely through the lens of a physicist.
Which brings us to Section 1, the science of work. You see, in science, doing actual work requires two extremely specific things, a force and a displacement. But oh, here is the catch. That displacement absolutely must be in the exact same direction as the force you're applying. We calculate this pretty simply as W equals F times S. W is work, F is the constant force applied, and S is the displacement. Bottom line, if you don't have both force and displacement moving in the exact same direction, you don't have work.
To visualize this, just imagine lifting a single 5-kilogram bag of wheat. Now, to lift it smoothly, you've got to apply an upward force equal to gravity pulling down on that bag. As you raise it exactly 1 meter straight up into the air, your upward force and the bag's upward displacement are completely perfectly aligned. Boom! You have successfully done work.
Now let's scale this up a bit. If you take 3 bags together and lift them to that exact same height of 1 meter, well, the mass is tripled. Therefore, you have to apply 3 times the upward force to overcome gravity. Because the displacement remained exactly the same, but your force tripled, it means you've just done 3 times the work. It's a direct, proportional relationship. And similarly, let's say you go back to lifting just that 1 bag, but this time you hoist it 3 meters high instead of 1. Now you're applying that original force, but over 3 times the distance. That increased distance means you've, once again, proportionally tripled the work done. So the absolutely crucial takeaway here is that applying a larger force over the same distance or applying the same force over a larger distance, both of these allow you to proportionally do way more work. All right, now that we've got the basic rules and the formula down, let's fully solve that mystery of our brick wall from the beginning of this explainer.
Moving on to Section 2, when work is 0.
Let's look at the math for a second. Work equals force times displacement, right? So if a wall doesn't move when you push it, the displacement is 0, and anything multiplied by 0 is, well, 0, meaning the scientific work done on the wall is a big fat 0. Now, sure, you still feel tired because your muscles are repeatedly expanding and contracting to apply that force, burning up your internal energy. But from the wall's perspective, nothing happened. No work was received.
Furthermore, displacement can actually happen, but if the direction is wrong, the work is still 0. Think about carrying a heavy box while walking forward at a steady pace. You're constantly applying an upward force just to balance the weight of the box against gravity, right? But the box itself is moving horizontally. Because your upward force is perpendicular to your forward motion, incredibly, you are doing strictly 0 scientific work on the box as you walk. Wild, right? So work isn't just about raw effort, it is heavily dependent on direction. Which leads us to the fact that yes, negative work is a totally real mathematical concept in physics.
And that perfectly sets up Section 3, positive and negative work.
So positive work happens when force and displacement share the exact same direction. For instance, if you're pushing a wheelchair forward, your pushing force and the chair's forward movement align perfectly. That right there is positive work. But negative work occurs when the force and the displacement directly oppose each other. A perfect, everyday example of negative work is a goalkeeper catching a football. Think about it. The ball is displacing forward, zooming towards the goal.
The goalkeeper puts their hands out and applies a force in the opposite direction, pushing back against the ball to slow it down. Because that force is opposite to the displacement, the goalkeeper does negative work on the ball. Okay, so we've established how to define work, calculate it, and how direction determines if it's positive or negative. But what does work actually do to an object?
Let's find out in Section 4, the work-energy theorem.
To really understand this, we need to talk about energy. Simply put, energy is the capacity to do work. When work is done, energy is actually transferred. And energy comes in so many incredible forms all across the universe. We've got thermal, heat energy, light energy, the chemical energy stored in our food that powers our muscles, electrical energy, and of course, mechanical energy, which is the energy of motion and position. But for our mechanical purposes today, we rely on a truly brilliant scientific principle. The work-energy theorem elegantly states that the work done on an object is exactly equal to the change in its energy. It's that simple. If you do positive work on an object, you literally give it energy. If you do negative work on an object, you are taking energy away from it.
Think of playing a game of carom or even billiards to really see how this transfer happens. You flick the striker. That moving striker hits a stationary coin. The striker pushes the coin in the direction of its motion, doing positive work and transferring energy to speed that coin up. But simultaneously, thanks to Newton's third law, that coin pushes right back on the striker in the exact opposite direction. It does negative work on the striker, taking energy away and slowing the striker down. It's a perfectly balanced transfer of energy. And that brings us to the very specific energy of motion.
Welcome to Section 5, Kinetic Energy and Motion.
Mechanical energy that is caused strictly by an object's motion is called kinetic energy. A moving bicycle, a rolling ball, a speeding car, they all possess kinetic energy simply because they're moving. If an object is just sitting there at rest, its kinetic energy is zero, period. It only gains this kinetic energy when positive work is applied to it to get it moving in the first place.
So, how do we actually measure this? Well, we combine what we know. We start with our classic motion equation, and we inject our brand new definition of work. Next, we substitute Newton's famous second law, force equals mass times acceleration, right into the mix. When we blend all these formulas together, we arrive at this beautiful mathematical realization. The change in kinetic energy equals 1/2 mass times final velocity squared minus 1/2 mass times initial velocity squared.
And you know, this brilliantly illustrates a slightly terrifying truth about driving a car. Just look closely at the formula. The velocity term is squared. This means that if a moving car's velocity simply doubles, its kinetic energy doesn't just double, it quadruples. Because of that, it requires 4 times the amount of negative work from the brakes to actually stop it, and a crash at that doubled speed involves 4 times the energy transfer. It's honestly an incredible real-world consequence of just one tiny little exponent in a physics equation.
Now, to leave you pondering your newly acquired physics lens, let's take a look at a playground. We have slides here of all different heights, shapes, and curves. Based on the work-energy theorem we just learned and the idea of gaining kinetic energy as you move downward under the constant force of gravity, which of these slides will actually result in the highest speed for a child reaching the bottom? Does the steepness matter, or is it purely about the vertical displacement?
I'll let you think about how distance, applied force, work, and kinetic energy all connect in that playground. Once you start seeing the world through equations, like work equals force times displacement, you realize physics isn't just trapped in a textbook. It governs literally every single thing we do. Keep looking for the hidden physics in your everyday life. And hey, thank you so much for joining me on this explainer.